Signals and Systems, Laplace Transforms, Problems, second part. Series on Signals and Systems, lecture number 4.14. In the present session, our focus is on determining inverse Laplace transforms of certain frequency domain signals. Here, we mainly demonstrate the application of partial fraction expansion method. Now, let us move into the core session. Before going to the actual problems and their solutions, let us spend some time on the definition of Laplace transform. Two types of transforms are there, bilateral and unilateral. Bilateral is also known as a two-sided transform. Unilateral is known as one-sided transform. Unless otherwise specified, it is only unilateral transform. Bilateral transform is used rarely. When it comes to defining relations, bilateral Laplace transform of a signal f of t it is designated as f of s. It is equal to integral minus infinity to plus infinity f of t e power minus st dt. If the lower limit on the integral sign is 0, then it becomes unilateral. Third relation is inverse transform. It gives f of t from f of s. F of t is equal to 1 by 2 pi j integral sigma minus j infinity to sigma plus j infinity f of s e power st ds. Note, in Laplace transforms, the transform variable is s. S is known as complex frequency. It is related to real frequency through the relation s equal to sigma plus j omega. Omega is real frequency. Sigma indicates attenuation. S is therefore a complex quantity, complex frequency. Before moving further, one or two important points regarding Laplace transforms. Laplace transforms, they convert integral convolutions and differential equations into algebraic equations. Algebraic equations are easy, simple, less difficulty to deal with. Hence, while converting integral and differential equations into algebraic equations, Laplace transforms make our life easy and comfortable, also convenient. Laplace transform is a more general form, and Fourier transform is just a special case obtained by letting s equal to j omega. By letting sigma equal to 0 in s, one can get Fourier transform. Before going to actual problem solutions, we also need to consider another aspect, another method which we are going to use in solving the problems in the present session, that is partial fraction expansion method. A few points, important points, they are being mentioned here. Let us consider a rational function. What is a rational function? It is one which is a ratio of two polynomials. That's all. Definition is as simple as that. Here we consider a rational function f of s equal to a n s power n plus a n minus 1 s power n minus 1 plus etc. plus a1 s plus a naught. This is an nth order polynomial, numerator polynomial. It is denoted, it is named as n of s. In the denominator, we have another polynomial. It is s power m plus b m minus 1 s power m minus 1 plus etc. plus b1 s plus b naught. It is the mth order polynomial. It is designated as d of s. So f of s is numerator polynomial n of s by denominator polynomial d of s. N and m are orders of the polynomials n and d, n of s and d of s. When n is more than or equal to m, then the function f of s is called improper. If n is less than m, then it is called proper. If f of s is improper, then it can be expressed as a sum of polynomials in the positive powers of s and a proper fraction. The inverse transforms of the polynomials in the positive powers of s are singularity functions. Inverse transform of s is impulse. Inverse transform of s power n is nth differential of impulse function. The proper fraction can then be expressed as a sum of simple fractions for which inverse transforms can simply written down by mere observation. The denominator of the fraction may have all simple roots or multiple order roots or combination of both types. When some roots are simple and some are multiple, then procedure is combination of the first two. Let us suppose it has only simple roots. Then the proper fraction, it can be expressed as f of s equal to c1 by s minus s1 plus c2 by s minus s2 plus etc. plus cr by s minus sr etc. plus cm by s minus sm. And cr, these quotients c1, c2, cr, cm, they can be computed using the relation cr equal to f of s minus sr at s equal to sr. When the proper fraction consists of multiple order roots, then how to expand? Let f of s is equal to n of s by d of s equal to n of s by d1 of s into s minus s naught power n. This s minus s naught power n, this has to be expanded like k naught by s minus s naught power n plus k1 by s minus s naught power n minus 1 plus etc. kn minus 1 by s minus s naught, and the remaining part d1s, it has to be expanded as c1 by s minus s1 plus c2 by s minus s2 plus etc. cr by s minus sr plus etc. cm by s minus. Here kj is 1 by j factorial, jth differential of f of s multiplied by s minus s naught power n with s equal to s naught, and cr is product of f of s multiplied by s minus sr at s equal to sr. So this is the framework of partial fraction expansion method. Before going further, let us recollect the important aspects, useful aspects pertaining to this method. There is a rational function. It can be improper, it can be proper. If it is improper, we have to convert it into a proper function plus some polynomial consisting of expression in s and its powers. Inverse transform of s square s cube can be had from impulse function and its derivatives. So for that part, inverse transform can be obtained without much difficulty. Now the proper function part is to be considered to obtain inverse transform. This part may have simple roots, only simple roots for its denominator, or the denominator may be of multiple order roots. Another possibility is some roots are simple, some are multiple. If roots are all simple, then the expansion is given here, first expression. If roots are of multiple order, then second one. In fact, second one explains, gives information when the denominator has certain number of simple roots and a certain number of multiple roots. So using the expressions provided here, one can expand the given rational function into partial fractions. From partial fractions, one can simply write down inverse Laplace transforms. While writing down, the following relations are quite useful. Laplace transform of t power n u of t, it is equal to factorial n by s power n plus 1. Laplace transform of t power n e power at u of t, it is n factorial by s minus a power n plus 1. Now we consider problem. Derive inverse Laplace transform of the given function. Function is f of s is equal to 3s plus 10 divided by s square plus 7s plus 12. First, what we need to do is we have to expand the given function, given signal in simple functions, first order functions, using partial fraction expansion method. Fs can be expanded and we get Fs equal to 1 by s plus 3 plus 2 by s plus 4. Inverse transform of 1 by s plus 3 is e power minus 3t u of t. Inverse transform of 2 by s plus 4 is 2 e power minus 4t u of t. So here key to the solution is usage of partial fraction expansion method to convert this somewhat complicated second order function into simple functions. Another problem. Derive inverse Laplace transform of the given function f of s, which is equal to 2s plus 9 by s square plus 4s plus 29. Procedure is same. First write down s square plus 4s plus 29 to factors. The factors can be found as s plus 2 plus j5, s plus 2 minus j5. Then go for partial fraction expansion method. It results in f of s as 2 plus j by 2 s plus 2 plus 5j plus 2 minus j by 2 s plus 2 minus 5j. Now we have inverse transform for s plus 2 plus 5j. We have inverse transform s plus 2 minus 5j. Both are in the denominator. So 1 by s plus 2 plus 5j, 1 by s plus 2 minus 5 minus 5j or j5. For both we have inverse transforms. From the tables we can get them and use them to get inverse transform of fs, f of t as e power minus 2t, 2 cos 5t. plus sine 5t multiplied by u of t. Another problem, derive inverse Laplace transform of the given function. Earlier two are simple problems when compared to the present problem. Notice lot of complexity is there. F of s is equal to 4s cube plus 16s square plus 23s plus 13 by s plus 1 cube multiplied by s plus. Procedure is the same using partial fraction expansion method. F of s can be written as c1 by s plus 1 cube plus c2 by s plus 1 square plus c3 by s plus 1 plus c4 by s. C1, C2, C3, C4. They can be found. C1 is equal to 2, C2 is 1, C3 is 3, C4 is 1 in the present case. Applying inverse transform both sides, f of s gives f of t, and the four fractions, they give inverse transform of f of s as u of t multiplied by t square plus t plus 3 e power minus t plus e power minus 2t. Getting the final result from the partial fractions is quite easy, quite simple. It doesn't require any explanation. Another problem, derive inverse Laplace transform of the given function. F of s is equal to 4s plus 13 by s plus 1 multiplied by s plus 2 whole square. Again, partial fraction expansion. F of s can be expanded as c1 by s plus 2 whole square plus c2 by s plus 2 plus c3 by s plus 1. C1 can be determined from s plus 2 whole square f of s with the s tending to 0. It turns out to be 8. C2, it is d by ds, s plus 2 whole square f of s tending to 0. It turns out to be 4. Similarly, C3 can be found as 4. Substituting results in f of s as 8 by s plus 2 whole square plus 4 by s plus minus 4 by s plus 1. Applying Laplace transform, inverse Laplace transform, both sides, use f of t equal to 8t e power minus 2t plus 4 e power minus 2t minus 4 e power minus t multiplied by u of t. Here u is unit step function. Another problem, derive inverse Laplace transform of the given function. F of s equal to 10s square e power minus s by s plus 1 multiplied by s plus 3. Solution. Now expand f of s by e power minus s in partial fractions. F of s by e power minus s gives us 10s square by s plus 1 s plus 3. It can be written as 10 minus 40s plus 30 by s square plus 4s plus 3. This 40s plus 30 by s square plus 4s plus 3. It can be expanded into partial fractions 9 by s plus 3 minus 1 by s plus 1. Therefore, f of s becomes equal to 10 minus 5, 9 by s plus 3 minus 1 by s plus 1, e power minus s. Applying inverse transform on both sides results in f of t equal to 10 delta t minus 1 minus 5, 9 e power minus 3 t minus 1 minus e power minus t minus 1 whole thing u of t minus 1. So this is the solution result. Another problem, derive inverse Laplace transform of the function f of s given by s by s plus 3 multiplied by s square plus 4s plus 5 using partial fraction expansion. F of s is can be written as s by s plus 3 s plus 2 plus j s plus 2 minus j, and this function then can be expressed as combination of three partial fractions. They turn out to be minus 3 by 2 s plus by s plus 3 plus 3 minus j by 4 by s plus 2 plus j plus 3 plus j by 4 divided by s plus 2 minus j. Applying inverse transform both sides gives us left side f of t, right side minus 3 by 2 e power minus 3t plus 3 minus j by 4 e power minus 2 plus jt plus 3 plus j by 4 e power minus 2 minus jt. This can be further simplified. Another problem, derive inverse Laplace transform of the function f of s given by s plus 5 by s square multiplied by s plus 2. Using partial fraction expansion method, f of s can be written as c1 by s square plus c2 by s plus c3 by s plus 2. c1 here is equal to s square f of s tends to 0. It turns out to be 5 by 2. C2 is d by ds s square f of s tends to 0. It turns out to be minus 3 by 4 and C3 3 by 4. So f of s can be written as 5 by 2s square minus 3 by 4s plus 3 by 4s plus 2. Applying inverse transform both sides, we get f of t equal to 5 by 2t minus 3 by 4 plus 3 by 4 e power minus 2t u of t. With this problem, we come to the conclusion of the present session. In the session, mainly the focus is on deriving or getting or finding inverse Laplace transforms of functions, frequency domain functions, using partial fraction expansion method. Hope this session is useful to you. We meet again in another session very soon.